Hello everyone, thanks for coming. Today we are going to do a review of our week 7's lectures. So in this week we talk about the gradient and then we talk about extreme values of a multivariate function. For function of multiple variables, the gradient is simply the vector of all partial derivatives fx1, fx2 to fxn. The directional derivative can be defined using the concept of gradient. The directional derivative along a specified direction u is the inner product of f and u, where u is a unit vector. So here, a differentiable function at a point x0, y0 indicates that indicates the existence of the gradient and the directional derivative along any direction at this point, but not vice versa, which means that the existence of the gradient and directional derivative along a specified direction will not imply that the function is differentiable at a point. Next, we talk about the tangent plane for the level surface f of x, y, z equals to k, a constant, on a point p, x0, y0, z0 on that surface. So the tangent plane that passes through P is given as fx times x minus x0 plus fy times y minus y0 plus fz times z minus z0 equals to 0. So the plane has a normal vector partial f partial x, partial f partial y, and partial f partial z. The plane passes through the point P, so we have x minus x0, y minus y0, and z minus z0, as shown here. The maximum rate of change at the point P is just the norm of the gradient at P, x0, y0, z0. The maximum rate of change is actually achieved along the gradient direction, and this can be proved by using the Cauchy's inequality. So basically speaking, the level surface is perpendicular to the maximum rate of change, which means that if we move along any curve that passes through the point P on the surface, then the value of the function f will not change, and the maximum rate of change, the direction of it, is always perpendicular to the tangent plane. Then, with the directional derivative and the gradient, we can talk about local minimum and local maximum. For differentiable functions, all partial derivatives at points where local minimum and maximum values are taken are all 0. However, if on a point all partial derivatives are 0, then that does not mean that the point is the point where the function takes its local minimum and maximum. Those points where all partial derivatives are 0 are called critical points. However, we need to perform second derivative test to determine if the function takes its local minimums and maximum on those critical points. We need to do the second derivative test. Let d be fxx fyy minus fxy squared. If d is greater than 0 and fxx is greater than 0, then fab is a local minimum. If d is greater than 0 and fxx is smaller than 0, then fab is a local maximum. So this is like the delta for the second order equation. If d is smaller than 0, then fab is not a local maximum or minimum, and nothing can be derived here. However, for continuous functions, we can talk about its absolute minimum and maximum on a compactly supported set. So if a continuous function is defined in a compactly supported set, it achieves its minimum, absolute minimum, and maximum on that set. So how to obtain those absolute minimum and maximum? We need to compare boundary values at values in critical points and then to determine minimum and maximum. in the absolute sense. Thanks for listening.